This is a video from section 3.9 and it's on related rates. We're going to look at another example. The sides of an equilateral triangle are increasing at a rate of 10 centimeters per minute. At what rate is the area of the triangle increasing when the sides are 30 centimeters long? Okay, so what we're going to do is we're going to let x equal the side of an equilateral triangle. And equilateral triangle just means all the sides have the same length. Now, what we need to do is we need to derive the area. So we're going to let A be the area of the triangle. So I'm going to show you how to derive that area. So let's draw a triangle here. And then we'll start writing down the information. So here's x, here's x, here's x. So they all have side length x. And so what I'm going to do is I'm going to drop a perpendicular down. And from geometry, what that does is that cuts this bottom side into two equal parts. So this side is of side length 1/2 x. And we'll call that this length, this dotted length here, we'll call that h. Now, from the Pythagorean theorem, we know that 1/2 x squared plus h squared is equal to x squared. But 1/2 x squared, quantity squared, is 1/4 x squared. Plus h squared, that's equal to x squared. So h squared is 3/4 x squared. So if I solve for h, I claim h is the square root of 3 over 2x. Now, what does that mean? That says the area is 1/2 the base, which is x, multiplied by the height, but the height is square root of 3 over 2x. And so therefore, A is square root of 3 over 4 x squared. Now, let's go back to the problem. So what do we know? The sides of the equilateral triangle are increasing at a rate of 10 centimeters per minute. So we know dx dt is 10 centimeters per minute. Now, the question says, at what rate is the area of the triangle increasing? So we need to think of derivative when the sides are 30 centimeters long. So we want dA dt when x is 30 centimeters. And so what we want to do is we want to start with A, which is square root of 3 over 4 x squared. dA dt is equal to square root of 3 over 2x times dx dt. And so what I'm going to do is I'm going to replace dx dt with 10 centimeters per minute. And I'm going to replace x with 30 centimeters. And so therefore, dA dt is square root of 3 over 2. I'm going to multiply by x, which is 30. And then I'm going to multiply by dx dt, which is 10. And so when I multiply all that out, I get 150 root 3. And so that says the area of the triangle. And remember, we got a positive result, which means it's increasing. If we got a negative result, that would mean the triangle is decreasing. So the area of the triangle is increasing at a rate of 150 root 3 square centimeters per minute. The units of area are square centimeters. The units of time in this problem happen to be minutes. And that's how you do example 1. Let's go ahead and look at example 2. The length of a rectangle is increasing at a rate of 8 centimeters per second, and its width is increasing at a rate of 3 centimeters per second, so we should be thinking of derivative. When the length is 20 centimeters and the width is 10 centimeters, how fast, rate of change, how fast is the area of the rectangle increasing? So, what we're going to do is we're going to let x equal the width of the rectangle. And we're going to let y equal the length of the rectangle. And let A equal the area. And so we have a rectangle. And so again, the length is 20 centimeters, but we're going to call that y for the moment. And this is x. So again, we're trying to find the rate of change when x and y take on specific values, right? Now, let's write down what we know. We know that the length is increasing at a rate of 8 centimeters per second. So we know dy dt is 8 centimeters per second. And we know dx dt, the width, is increasing at a rate of 3 centimeters per second. So we're going to write that here. Now, we want dA dt when? Now, when the width is 10 centimeters and the length is 20. So when y equals 20 centimeters and x is 10 centimeters. Okay, so that's what we're looking for. This is what we know, and this is what we want. Now, the area of a rectangle is x times y. Now, you're going to differentiate both sides with respect to time. That's the common theme when you're doing optimization problems. Okay? So, dA dt, and we're going to apply the product rule. So this is x times, here, let's do this. We'll take the derivative of the first, right, which is dx dt. And I'm going to multiply by y. And then I'm going to add x times dy dt. So this is just product rule. All right? Now, let's go back. dx dt is 3. So I'm going to put a 3 there. So this is 3 times y. And then dy dt is 8. So I'm going to put 8 times x. And so I'm going to say when y equals 20 and x equals 10, dA dt is 3 times 20 plus 8 times 10. But this is 60 plus 80, which is 140. Now, what does that say? That says the area of the rectangle is increasing at a rate of 140 square centimeters, right? That's the units of area. And the units of time in this problem is seconds. So it's 140 square centimeters per second. And that's how you do example 2, and that'll conclude this video for section 3.9. It's on related rates, and we did 2 additional examples. All right, thank you.